Now, we want to use extended separable ODEs to solve these two simple examples. Yeah. All right, so right now I'm making the second your exercise set for part B. Yeah, so I will post quickly, okay, part B. After that, I will post solutions to part A. Then part C. Today we almost finished part C. So I can start working, you can see a lot of work. Yeah, a lot of work. Yeah. All right, so let's, oh, yeah, okay, it works. Yeah, 2 questions. Let's solve the first one. Yeah. First one, here, we want to use separable method to solve it. But if you look at the form directly, not separable, right? Not directly separable. So we want to do some manipulation, transformation, to make it to be separable in some special way. All right, so I hope you can still remember a little bit what we learned last time, but I will remind you. Yeah. All right. First, because this form is not our standard explicit form, right? Our standard explicit form should be y prime equals f function. Y prime equals some expression. So let's write y prime equals certain expression first. All right. So after simple algebra, division over 2xy. So you get this y prime expression. Yeah. This one, yeah. When you see this one, can you see some special properties in the right-hand side expression? Special property. Any special property you can see? Right. Oh, okay. Yeah, common denominator. Yeah, all right. Yeah. Any other observation? Some interesting property could be useful. All right. Here, let me tell you. You look at the degree of each term. You know degree, right? Here we call total degree. Degree. What's degree? Degree. Here, degree of this term, y term, 2, right? Degree of x, 2. Degree of this term, x has 1 contribution, y has 1 contribution. So we call the total degree. You add up 1 plus 1, also 2. Now tell me, what's the property you can see based on the degree property? Degree property. Numerator, denominator, same degree, right? Degree all 2. That's the property. Okay? So why this property is useful? Total degree 2. And actually, let me give you, more specific. Each term has degree 2. How about that? All terms are of degree 2. How about that? That property. Is that interesting? All terms have the same degree 2. Okay, that property. Yeah. That property, yeah, because then we can take division term by term. Denominator only 1 term, all right? So split. Numerator 2 terms, let's split them term by term, okay? Yeah, 2 separate terms. And do some cancellation. You get this form, right? Yeah. You get this form, all right? Now, can you see the pattern, y over x pattern? Y over x pattern that we can take advantage of in the method we discussed last time? Y over x. F of y over x. Remember the last time? So here, let's recall. Where is my pen? Where is my pen? See? I check it, remember? Oh, here, in my pocket. All right, so now I can write it on my screen. Yeah. Here I'm talking about y over x. Can you see this form? Y over x. This is the one we discussed last time. When we see this form, we can introduce a new variable represent y over x. How close compare our current expression compare with this f of y over x function? How close is it? Are they? How close are they? Okay. The first term, no problem, right? So check it. How about second term? Yeah. Again? See?
Inverse.
Oh, yeah. So you use that term, inverse, but we call reciprocal, right? Just the reciprocal of y over x. Reciprocal. Okay? Yeah? If reciprocal, if we let y over x u, then x over y just 1 over u. Reciprocal. Okay? All right? Yeah. So try to be sensitive on those expressions. Oh, drop it. Yeah. All right. Let u equals y over x. Now let's rewrite y prime. This time equals, y prime. All right. So here, y prime, we have two ways to get a y prime, right? We have two ways to get y prime. One way, we just take, because, here, I skip something, but let me write the part that I skip it, okay? Yeah. So, because this expression tells us y equals u times x, right? Then we take prime both sides, but this one by chain rule. Derivative, the chain rule of derivative. Oh, not chain rule, sorry. Product rule, right? Yeah. Because it's a product. Yeah, chain rule we will use later. Product rule. Yeah, okay? So by product rule, we get this. Yeah, u prime x times u x prime. X prime is 1, okay? So that's why u prime x plus u. That's our first y prime representation. Second, use u to represent right-hand side of our previous equation. U, yeah? So second representation. So we have two representations. All right, yeah, 2. The second one, u over 2 minus 1 over 2u. Now, if we look at the, u prime x plus u equal, we can ignore y prime because we want to solve a new equation without any y involved. Without any y involved. Because u replaces y. We don't want both u and y appear in the new equation. So that's why this time we just look at this new equation with u and x and solving for u. Solve it for u function. All right. Yeah, so let's do another cleanup work, okay? Cleanup work. You know, left-hand side u prime x, right-hand side all u terms. All u terms. Then, this time, separable form, very clear, right? This time, you can identify it's separable, right? Yeah. So let's write one more step to get it. Yeah. I mean, this just, you know, for some convenient format. Okay. Yeah. Yeah. All right. Then make it separable version. Left-hand side, all u terms. Right-hand side, all x terms. By some simple algebra operations. Okay? Yeah. Now, I think you have confidence to solve after all these steps, this kind of work, then now you have the confidence to solve it. All right? Yeah. Practice, complete the solution. Yeah. Complete the solution. Okay? Yeah. Yeah. Before I skip, do you know, yeah, because this part is easy, right? Do you know how to find the integral of this one? Any idea? Integral? Substitution? Yeah, although we can do what substitution you want to do? Denominator? Oh, good. Yeah, pretty good. All right, pretty good. Yeah. So all of you want to do substitution? Okay, all right. Yeah, because for me, I want to skip that substitution. Okay? Yeah, although it's okay, but for me, I write it to du squared. Can you see du squared plus u squared plus 1? Du squared. Can you do the, I pull this 2u, I pull into the d operator, d derivative, right? So du squared, that is u, you know, by the power rule, 2u du, right? Can you see it? I don't know if you feel comfortable. Yeah. If you feel comfortable, when you move outside u term, inside d, but you need to consider the derivative operation. Okay? Derivative. Yeah. Yeah. All right. Then, this one, I use another operation we used before. When we add a constant inside d, it's legal. Because derivative of a constant is always 0, right? So I use this all the time. Inside the parenthesis, I add a constant. Try to make denominator and parenthesis, inside parenthesis part the same. So I add that. I can add any constant free inside differential. Because the constant differential of constant always 0. So I add 0, no problem, right? I just add 0. Okay? It is balanced. Yeah. So here, I talk about this kind of detail because for some computation, yeah, I use my own way. I can do it very fast. Okay? If you practice a lot, so if you establish the thinking like this, so you can do your work very fast. All right? Yeah. So here, I just do a few examples to show you. After we do this, do you know what's the integral of this one? Can you see it immediately? Are you familiar with the basic integration formula? This one, can you write it out immediately? Right, natural log. Good. That's good. Natural log of what? Natural log of what? Right, denominator. But the denominator here, one point I want teach you to be careful. Denominator, the original formula is the absolute value of the denominator, right? For example, if you write this one, we can also use that same formula, right? This one should be negative natural log of absolute value of x, right? If you write natural log of x, it's wrong, okay? So the standard formula here, when you write integration of this one, don't forget, put the absolute value here, okay? Don't forget, okay? You may get wrong, right? That's important. But here, do we need to put an absolute value? No, because we know 1 plus u squared always positive. 1 plus u squared, always positive. So you just write u squared plus 1, okay? Always positive, right? Yeah, so, all right, yeah, so. All right, so we finish this one. Yeah. Next, solution for the second question. This time, before we do anything on it, not separable, right? Not separable. Yeah. So if, when you look at the first side, not separable, the next thing you consider how to do some appropriate substitution to make it separable. Yeah, make it separable. Yeah. Do you have an idea to introduce a new variable to make it separable? New variable. Let u inside whole thing inside a parenthesis, y plus 4x. Y plus 4x. Okay? Yeah. Then take derivative. U prime, yeah. U prime equals y prime plus 4, then we just write y prime equals u prime minus 4. Minus 4. Okay. Simple algebra here. Then let's go back to the original equation. Original equation, y prime give us u squared. Yeah, that's this one. Okay. Then we can ignore y prime, only work on the new differential equation, u prime minus 4 equals u squared. That's separable. Okay? All right. This time, after the form change, we get this one. Okay? Yeah. Then we can just do the integral. We can find the solution. Okay. Do you know how to do the integral here? Yeah. So here I just use I do the detail for review. Yeah. Although I use a little more time, review a little bit. See if you're familiar with the basic formulas for the integration. Basic formulas.
Should we add like constant C?
Constant C.
Like at the end, we solve it.
Integration. Yeah. All right. So here. Let's do this. du over u squared plus 4. Okay? But there is one formula you need to know before you do this. Here, there is a 4. The standard formula is du over 1 plus u squared. Yeah. U squared plus 1 or 1 plus u squared. So whatever, 1 plus u squared. Do you see any formula? Right, tan, related to tan something. Arctangent or inverse, tangent inverse or arctangent. Yeah, two different. You use arctangent inverse, right? Which one you prefer? Inverse or arctangent? Arctangent? Both? Yeah. Let me write two forms. So one is tan inverse of u. Another is people also write arctangent u. Equivalent. These two forms equivalent. Yeah. In your calculus, which one you use? Inverse or arctangent? Oh, yeah. All right, whatever. For you, you just choose one of the two. Okay? Yeah, for me, both is fine. Yeah. Arctangent means inverse. Okay? The same thing. Yeah. Arctangent. Yeah. But inverse, don't understand inverse as the reciprocal. That would be wrong. Okay? Here, tangent inverse does not mean the reciprocal of tangent. That's completely wrong. So you may confused. You may get confused if you use tan inverse. Think about that. I worry some of you may write tan, the inverse function x as, but it actually, be careful, reciprocal of tan. That would be wrong. All right? That would be, it's not reciprocal. Okay? Reciprocal, yeah. If you write reciprocal, you should write this form. Reciprocal, so this reciprocal, you write the whole tan inverse. That's reciprocal. Okay? The whole tangent x, parenthesis to the -1. That's reciprocal. Okay? Do not get confused. You put in this place, that means inverse function. Similarly, for sine, cosine, we follow this rule. Okay? Follow this convention. Yeah. Yeah. Do not get yourselves confused. Yeah. So these little things, at early stage I mention. Later stage, I won't mention that. Okay? All right. Yeah, so now you know arctangent or how to use that arctangent formula to calculate this one. There is a 4, so you cannot apply directly. If I apply directly, you know, because the formula is on 1, not on 4. It's on 1. Constant term is 1, not 4. So you need to do transformation to get a new expression using 1 in that constant location. Yeah, let me show you the technique, the basic technique. The numerator 4, can we factor numerator 4 out? Factor, yeah. So factor that numerator 4 out. Du 1 plus u over 2 square. Can you see this? 1, 4, take it out. So 1 left inside parenthesis. U square, you need to use it divided by 4, right? But there is square, so I want to put that 2 inside u. I put that 2 inside u. Okay? All right. Another step. Yeah. Because inside parenthesis, u over 2, but inside the d, that's u. It's different. Okay? du, it's u. But this one, u over 2, they are different. So I cannot apply the original formula. I need to do one more step to make the part inside u and the part inside the lower parenthesis exactly the same. Then I can apply the formula. Okay? How to make that? So I do this way. 1/4, I split as 1/2 times 1/2. How about that? 1/2. So I still have 1/2 here. The other 1/2, can I move it inside the D? Can I move the second 1/2 inside that D? You may feel weird. Is it weird? Is the manipulation weird? Yeah, yeah. I hope you get used to it. Yeah. All right. Because here, one thing, any constant outside, you can move into D operator directly. Okay? It's a constant. Move in, move out. Okay? Here outside we have 1/2. We bring it in. Free. Okay? No problem. Legal. Yeah. All right. After we move in, this time you see 1 plus u over 2 squared. Right? This new form. Does it match our original formula? Just replace u by u over 2. Does it match exact form of the original formula? Yes. Huh? So the last step, we write the answer. Assume if you use arctangent, u over 2. Okay? Yeah. If you use inverse, let me separate. Inverse 1/2 tan inverse u over 2. Okay? How about that? How about that? Yeah. So here the basic simple calculation. Yeah, the reason I spend 10-something minutes, so I want at the early time I want everybody, you should be familiar with these basic operations. Do you feel you need to practice a little bit? Yeah. So I'm thinking about how to help you practice these basic things because that's the foundation. Otherwise, later, when you solve differential equations, you get stuck. So last step, integration, you get stuck. So, but I haven't found idea how to help you practice these basic things. Yeah. I'm thinking about it. Yes, yeah. Right, yeah, formula sheets. Yeah. Yeah. No problem. Yeah.
As long as, like you mentioned, the equations we need for various solutions, like I will put it down.
Yeah. Yeah, yes. Yeah, have it. Everything, all learning materials are legal. You can use. Not just sheet, not formula sheets, solutions, whatever, all legal. Okay? Yeah, everything. Yeah. All right. Yeah. Then I want to move a little faster. Yeah. So we finish part B. Yeah. This is the last slide of part B. Okay. Yeah. Question?
So without your answer, would you just substitute back into Q?
Yeah, substitute back, right. Substitute, yeah, answer. Yeah, you're right. The answer, we want to find the y function, right? Answer, we want to find the right function. Yeah, answer, we need to do a few more steps. Yeah, definitely. Yeah, here. Yeah, I do not have the space. Yeah. All right. Yeah, let me do it on whiteboard. Okay. Yeah. I have to have a good one. Good marker. Oh, this one good. All right. So the answer, remember, so we're here, we find integration. Yeah, let's use that. Okay? Yeah. So left hand side, 1/2 arc tan u over 2 equals right-hand side, just x plus c. That constant c. Don't forget that constant c. Okay? All right. Let's do some change, make it better. Okay? Yeah. Arc tan u over 2 equals 2x plus 2c. Right? Yeah. 2c. Okay? All right. Then, inverse. So then we have u over 2 equals tangent of 2x plus 2c. Okay? Then we have u equals 2 times tangent 2x plus 2c. Can you see that? U expression in terms of x expression. And we know u equals y plus 4x. So the final solution, we need to write y equals 2 tangent 2x plus 2c plus minus, right, 4x. Okay? Minus, yeah. But there is one more step, but that step, just improve it slightly. What do you mean 2c here? Yeah, just c, yeah. You got it. Perfect. Because c is arbitrary constant, 2c and c. 2c also arbitrary constant, right? C also arbitrary constant. Why we use 2c, right? So that's the point. Yeah. So very good. So we like the simplification. We like, further simplification. 2x plus just the c. Yeah, but some people, they want really good, rigorous math. So those people, they just use slightly different notation, like c star, okay? Plus minus 4x. Yeah. Because those people who really want rigorous math, they do not feel comfortable you replace 2c by c. Okay? Yeah. So they just use a slightly different notation. C star. Okay? Yeah. So that's how we write the final solution. Okay? If there is some initial condition, we need to determine this C star. Yeah, because the question, you may have some certain initial condition. What's the C star? So you plug in. When x equals 0, y equals 1, for example, so you solve for C star. Solve for C star. Okay? Yeah. That's the whole solution. Yeah. All right? Yeah. Okay? Yeah. All right. So let's move to part C. Yeah. If you have good idea how to practice the basic formula integration, mainly integration. So if you have a good idea, you can let me know. Yeah. All right. Yeah. All right. All right. Part C, exact ODEs. Another method. Yeah. This one, more complicated. Yeah, I hope you can follow. Yeah. The computation, more complicated. So now more and more complicated. When we learn more, we will work more and more complicated math. Yeah. This one you will see it. Yeah. But this one still not too bad. Yeah. C.1, exact ODEs. First, let me explain what's the meaning of exact ODEs. Yeah. All right. This time, so this part, we will develop another tool for solving the ordinary differential equations. Yeah. So here I give you the whole development process. Yeah. You try to follow, understand. After that, you can apply the formula. Okay? Yeah. After you completely understand it, then you are very comfortable. You can use the final formula to solve the differential equations. Yeah. Recall the explicit ODE form. We start from this one, this form. Okay? But this form still too general. Too general, it means could be very hard to solve. Okay? Then we just work on some special cases. Yeah. This time, let us work on another special case. So what special case? First, we want to consider f of x and y takes that fraction form. Numerator, denominator, m function over n function. That special case we consider. Okay? That case still also pretty general. Very general. Yeah. All right. So we write dy over dx form. Okay. This time we see differentials. Yeah. Yeah. Not this y prime. Y prime we cannot see differentials. In this form we can see differentials. Now we want to use differential to represent this form. You can see differential is very important here. This method relies on differentials. Otherwise, you cannot solve it. Okay? Critical. All right. Special property. Before we work on this form, I want to talk about some special property here. There is a concept called a total differential concept. I want to explain this total differential concept. Then we can understand this new method. So what's the total differential concept? Okay. All right. Consider an explicit function or curve with the form. So yeah, here we consider a special function, a general function. In this way, u of xy equals c. This equation, c is a constant. Now we consider this equation, or equation takes this form. Yeah. Because there is a special property built in this equation. So you may ask why you consider, because we know this method was developed by smart mathematicians. Those smart mathematicians, they discovered some smart way to manipulate functions. So here we just learn their way. Okay? All right. So this function, two-variable function, x, y, two-variable function. Okay? Yeah. So mixed in some arbitrary way. Yeah. Here, a simple example is x squared plus y squared equals 1. Do you know what is this equation? Are you familiar with that equation? X squared plus y squared equals 1. Circle. Perfect. Circle. Okay? Yeah. So the curve, we can draw a curve. Curve of that equation is a circle. Yeah. Unicircle, actually, right? The radius is 1, so it is a unicircle. Radius is 1. X, y coordinate. Okay? Yeah. And the left-hand side, that's our u function. U function. All right. Yeah. Here, yeah, so there is one simple question. Yeah. X squared plus y squared. Yeah. X squared plus y squared. Can we treat y as a function of x? So from this equation, can we treat y as a function of x? So here I check your understanding of function. Understanding of function. So my question is, can we treat y as a function of x? Yes or no? Okay, yeah. All right, so let me clarify. So I use this chance to, good, correct, okay, all right. Here, we should be very careful because given an x, if we draw a vertical bar, you get a 2 points, right? 2 intersection, 2 points of intersection. Yeah. That means given x, you have 2 different y's corresponding to x. Does it follow the definition of function? Yeah. For the function given an x, if you plug in, you can only get a 1 y value. That's the function definition. 1x corresponds to 1 y. Must be certain, not 2. 2 values. Okay? Yeah. So here, you can fix that hole. There is some problem. Fix that hole. You split the circle in 2 functions. Upper half circle, lower half circle. Okay? Upper half, thus. Can we treat upper half as a function? Yeah, no problem. Vertical line, 1 intersection point. And lower half, another second function. Okay? So y equals plus minus root 1 minus x squared, plus minus, plus part corresponds to one function, minus part corresponds to the second function. Okay? 2 different functions. Yeah. Yeah. So, but here I use this curve because when we use curve, so we do use function, so we avoid that problem. Okay? So if it's a function or not, it's a curve. The whole circle, a curve. Okay? Yeah. All right. Next, let's work on it. Yeah. We want to take the differential on the curve. So this is a curve. This whole equality represents a curve. It has left-hand side, it has right-hand side. Now, we want to take the differential operation on both sides and see what happens. We can do it, right? Yeah? Equality, we can take differential operation D, both sides. Right-hand side, what is the right-hand side? D of little c. What's the right-hand side? D of constant, what's that? 0. Yeah. So right-hand side is 0. Then we need to look at what's the form of the left-hand side. That's important. Yeah. What's the expression of the left-hand side? D. du. What's the du? Okay? All right. Yeah, right-hand side is 0, but we need to represent the du. Left-hand side, there is some special expression of the left-hand side. Okay, all right. The left-hand side, from du, that du, so we call it total differential. Yeah, because left-hand side is, several terms. That several term together corresponds to this du, so we call that expression total differential. Yeah. What's that? Du equals, we use partial derivative. partial derivative. Partial u over partial x times differential dx plus partial u over partial y times dy. Have you seen this formula before? Yeah. Recall a little bit, okay? Recall, yeah. Yeah. That's the, standard, straightforward, the formula. Yeah. So with this formula, now we want to consider the structure of this one, compare with that one. Now you can see this form, that form, they should have some similarity. We can explore here. Similarity. Okay? All right. So in the differential form, yeah, so we just do the cross product this way, move to one side. So we write it in this way. Okay? Compare that expression and this one. Can you see some structure-wise similarity? A little bit similarity, right? Yeah, yeah. All right. Yeah. So then we want to connect, because if we can connect, then we can use the structure here, because we know this is a total differential. du equals this whole thing. Total differential, right? So if that one matches this one, we can write the left-hand side as a total differential. How about that? That's the idea. We make connection. Total differential. Okay? All right. But something annoying here. This minus sign a little annoying, because here we have plus sign. Okay? First, we need to fix that minus sign. Yeah. We want this form matches our target one exactly. Exact match. Okay, so we want to change that minus sign. All right? Yeah. Can we make the change? Change minus sign to plus sign? Can we change it? Minus sign to plus sign? Because we really want to make the change. We force it. We force the change. Plus, how about plus minus n function? Is it okay? We put that minus sign inside parentheses. How about that? So we force it. Outside, you must take that plus sign, right? But you have extra minus. Let's bring it into that n function. Is it okay? Yeah, because n is a general function. We just multiply it by -1. Another general function, right? Yeah. So with this change, now we can consider this format, right? Yeah. Because we have a lot of freedom to determine that n. So we don't worry about that minus sign, right? So it's an easy fix. Easy fix. Yeah. All right. Now, plus sign there, plus sign here. So then we can try to match them term by term easily, right? At least the structure is correct. The structure is correct. We fix the structure. Yeah. All right. Yeah. Then, but we need to modify the original form. We put a negative sign in our original one. Then we fix it, right? Yeah. At the beginning, we consider, when we write that, let's just put a minus sign there. Then we will fix the sign problem. Okay? Yeah. All right. Now, after that, we can do analogy between these two expressions, right? This time, analogy. Okay? Try to match them. Try to match them, these two expressions. Yeah. But if you want to match these two expressions, you need to put some condition there, right? Yeah. You must enforce some certain condition. If you do not put any condition, then you cannot match them. Okay? Yeah. So next, we need to consider criterion for exact differential equations, the condition we want to enforce. Okay? So here, exact differential equation. So if we can write the left-hand side as a total differential, then we call that type of differential equation exact differential equations. Yeah. So when we see this general format, we want to ask ourselves, how do you know if there exists a u function such that du equals this expression? We wish to have, right? Yeah, that's our goal. That's our goal. Because if we can find that u, then this expression can be written as a total differential. This du is a total differential, right? Total differential du, then we can find that u, so we can get a solution uxy equals constant c, right? Yeah. Because if you can get this step, you can write a solution uxy equals c. You can write out a solution immediately. But we need to make sure we have this property. Yeah. So let's see what criteria do we need here. Okay. Why we consider uxy here? Yeah. Yeah. The answer is obvious. After discussion of the previous page, we consider total differential. It's obvious because we may have the implicit type of solution. This is implicit type solution, right? This is an implicit function, xy implicit. So we do not need to write y equals an expression of x. You do not have to write in that way. Okay? So we just keep the implicit form of the solution function. Okay? Implicit form. Yeah. All right. Implicit type of solutions for certain differential equations. Yeah. Yeah. So here we are looking for this type of solution for the differential equations to give us more freedom. To give us more freedom. Yeah. So if you always expect to have this kind of solution, then it's very restrictive, right? Yeah. If you always expect your solution for the differential equations should be y equals certain f of x, it's too hard because too restrictive. Many times we cannot do it. Now we want to relax that restriction. Okay? We want to make the restriction of this one weaker. So we consider a more general format. Because in this one, we don't have to write y in terms of x. It's hard. So we won't do it. Yeah. So if you can get this kind of solution, you solve the problem. You already solved the problem, right? You can draw the curve explicitly. You solve the problem. Yeah. So here we just consider this type of solution. So let's take a 10-minute break.